Hello students, welcome to your channel Parivartan Physics. See, we are in the series of videos where we are going through a course called as Rapid Revision course for KCET 2025. Right? So in this series of videos, we are learning the synopsis, the concepts, the shortcuts, the formulas of one chapter in one video. Right? So this is a quick revision of each chapter of physics to help you in KCET 2025. So all the chapters before this have been already uploaded. This is electromagnetic induction. So in this video, we are going to see electromagnetic induction. Okay. So without making any delay, let us begin with the video. And dear students, if you like the content of the channel, please don't forget to subscribe the channel and share the channel with your friends. Right? Okay. First, magnetic flux. See, we know very well magnetic flux means it is the number of field lines passing through a surface area normally. Expression for magnetic flux is NBA cos theta, where N is number of turns, B is magnetic field, A is surface area, and theta is the angle between normal to the surface and magnetic field, which we also call it as area vector. Area vector or normal to the surface and magnetic field, right? So if this is a surface area, see, if this is a surface area, for example, let me show you here. If this is a surface area and magnetic field lines are like this, then if the surface area is held like this, area vector will be like this. Area vector. Okay, so here will be the area vector. This is the normal or area vector, correct? So magnetic field and area vector both are perpendicular here. Sorry, parallel here. Suppose here area is perpendicular. Surface area is perpendicular to the magnetic field lines, but area vector is parallel to the magnetic field lines. So remember, in case of flux, if surface area is perpendicular to the magnetic field, then area vector or normal will be parallel to the magnetic field, and you have to take the angle between these two. Angle is substitute. If surface area is parallel to the magnetic field, then area vector will be perpendicular to the magnetic field. So you have to take angle is equal to 90 degree. So it is not the angle between surface area and magnetic field. If surface area hingadri magnetic field lines pass agate, I will show that magnetic field direction with the help of this finger. This finger namage magnetic field direction torsadatre. So magnetic field lines are perpendicular to the surface area, but area vector and magnetic field line, these both will be parallel. Area vector and magnetic field lines will be parallel. So you have to take the angle between area vector and magnetic field lines. It is not the angle between surface area and magnetic field, right? So this angle you have to take in place of that theta. Okay, that's all about magnetic flux. When do you say magnetic flux will change? Magnetic flux will change whenever number of turns changes, or magnetic field changes, or area changes, or orientation, angle changes. Since flux depends upon N, B, A and theta, if any one among these changes, then flux will change. Correct? And if flux changes, EMF will get induced in that coil. Right? So to get EMF, flux has to change. Flux change adre matra namagal EMF bartadre, otherwise you will not get the EMF. Correct? Okay, so induced EMF. So that EMF which is produced by change in flux, the EMF which get produced by the change in flux of the coil is called induced EMF. It is given by E is equal to minus d pi by dt by Faraday's and Lenz's law. Minus d pi by dt. In place of pi, I will substitute N B A cos theta. Right? If N is changing, you apply d by dt for N. You can write it like this: dN by dt, BA cos theta. If B is changing, you can write it like this: NA cos theta dB by dt. If A is changing, NB cos theta dA by dt. Like this, you have to go on applying d by dt for the quantity which is changing. Or final flux minus initial flux upon time. This will also give you EMF only, change in flux upon time. But d pi antandre it is change in flux, dt antandre it is time taken to change in flux. Next, how to find out the direction of the induced current? Induced current the direction yav ತರ ನಾವು find ಮಾಡಬೇಕು. ಈಗಲೇ ನೋಡ್ರಿ, here an inverse magnetic field is present. Cross mark ಅಂದ್ರೆ it indicates inverse magnetic field, right? ಆ magnetic field ನ external magnetic field ಅಂತ ಕರೀತೀನಿ. We are calling it as external magnetic field. And let me say this external magnetic field is increasing. See, here we are saying the external magnetic field is increasing. External magnetic field is increasing in the sense these field lines are increasing in the coil, right? Coil ದಾಗ ಅಷ್ಟೇ ಅಲ್ಲ, ಎಲ್ಲ ಕಡೆ ನಮಗೆ ಈ field lines ಏನಾಗ್ತಿರ್ತಾವ, they will be increasing, right? So if the external magnetic field is increasing, then it indicates that, it tells us that flux is also increasing, right? Flux, more number of lines are created inside the coil, then flux is increasing. If flux is increasing, then it will produce the induced EMF and induced current in that coil. A coil ಒಳಗೆ induced EMF ಮತ್ತು induced current produce ಆಗ್ತವೆ. So in which direction this induced current will be? ಯಾವ direction ಒಳಗೆ ಇದು induced current ಇರ್ತದೆ? See, if the flux or field is increasing, then this induced current and induced EMF must be in such a direction that they should oppose the increment of this external magnetic field. ಈ ಎಕ್ಸ್ಟರ್ನಲ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಅನ್ನು ಇನ್ಕ್ರೀಸ್ ಮಾಡಬೇಕು. ಆ ಎಕ್ಸ್ಟರ್ನಲ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಯಾವ ಡೈರೆಕ್ಷನ್ ಒಳಗದ? ಇನ್ವರ್ಸ್ ಡೈರೆಕ್ಷನ್ ಒಳಗದ್ರಿ. ಹಂಗಿದ್ರೆ ಆ ಇನ್ವರ್ಸ್ ಎಕ್ಸ್ಟರ್ನಲ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಏನ್ ಇನ್ಕ್ರೀಸ್ ಆಗತ್ತದೆ, ಆ ಇನ್ವರ್ಸ್ ಎಕ್ಸ್ಟರ್ನಲ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಅನ್ನು ಅಪೋಸ್ ಮಾಡ್ಲಿಕ್ಕೆ ವಿ ಶುಡ್ ಗೆಟ್ ಅನ್ ಔಟ್ವರ್ಡ್ಸ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್. ಆ ಇನ್ವರ್ಸ್ ಎಕ್ಸ್ಟರ್ನಲ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಏನ್ ನಮಗೆ ಇನ್ಕ್ರೀಸ್ ಆಗತ್ತದ್ರಲ್ಲ, ಅದನ್ನ ಅಪೋಸ್ ಮಾಡ್ಲಿಕ್ಕೆ ನಮಗೊಂದು ಔಟ್ವರ್ಡ್ಸ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಬೇಕು. This outwards magnetic field is not external magnetic field. It is not external magnetic field. External magnetic field is this one, inwards magnetic field. So ಇಲ್ಲಿ ನಾವು outwards magnetic field ಬೇಕಂತ ಹೇಳಿದ್ವಲ್ಲ, that is not the external magnetic field. That is the magnetic field produced by the induced current. That outwards magnetic field is produced by the induced current. The magnetic field which we are taking here to oppose the increment of the external magnetic field, that magnetic field is produced by this current. So according to this magnetic field, I will call this magnetic field as induced magnetic field. Then according to induced magnetic field, current in this coil has to be, induced current in this coil has to be anti-clockwise in direction. Current has to be anti-clockwise in direction. Idi niಮಗೆ ಗೊತ್ತಿರಲಿ, if the magnetic field lines are outwards, then the current will be anti-clockwise. If the magnetic field lines are inwards, then the current will be clockwise in direction. You remember this, right? So how did we get to know about the induced current direction here? It is anti-clockwise ಅಂತ ಹೆಂಗ್ ಗೊತ್ತಾಯ್ತು? Depending on the induced magnetic field, right? ಆ induced magnetic field basis ಮೇಲೆ ನಮಗೆ ಇದು anti-clockwise ಅದ ಅಂತ ಗೊತ್ತಾಯ್ತು. Induced magnetic field outwards ಬರಬೇಕಂತ ಹೆಂಗ್ ಗೊತ್ತಾಯ್ತು? Because the existing or external magnetic field which was already present, ಅಲ್ಲಿ ಮೊದಲು ಏನು ಎಲೆಕ್ಟ್ರಿಕ್ ಫೀಲ್ಡ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಇತ್ತಲ್ಲ, ಇನ್ವರ್ಸ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್, ಆ ಫೀಲ್ಡ್ ಇನ್ಕ್ರೀಸ್ ಆಗತ್ತದ್ರಿ. ಸೊ ಆ ಇನ್ಕ್ರಿಮೆಂಟ್ ಅನ್ನು ತಡಿಬೇಕು ನಾವು, ಆ ಇನ್ಕ್ರಿಮೆಂಟ್ ಅನ್ನು ಅಪೋಸ್ ಮಾಡಬೇಕು. ದಟ್ಸ್ ವೈ ವಿ ಟುಕ್ ಅ induced magnetic field in opposite direction of that original field, right? So depending on induced magnetic field, we'll put the direction of induced current. Okay, we'll take another case here. Again that magnetic field direction is same, cross mark, right? Magnetic field direction is same, but this time the magnetic field is decreasing. ಆ ಎಕ್ಸಿಸ್ಟಿಂಗ್ ಅಥವಾ ಎಕ್ಸ್ಟರ್ನಲ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಏನದಲ್ಲ, ಇದು ನಮಗೆ ಡಿಕ್ರೀಸ್ ಆಗುತ್ತದೆ. Decreasing in the sense what? One by one the lines are getting disappeared. One by one the lines are getting disappeared. So like this the magnetic field lines are getting decreased. If the magnetic field is decreasing, it clearly tells us that magnetic flux is decreasing. Magnetic flux is decreasing. If magnetic flux decreases, then again we say that flux has got changed. Flux increase ಆದ್ರೂ ಚೇಂಜ್ ಆದಂಗೆನೆ, ಫ್ಲಕ್ಸ್ ಡಿಕ್ರೀಸ್ ಆದ್ರೂ ಚೇಂಜ್ ಆದಂಗೆನೆ. ಅವಾಗ ನಮಗೆ ಮತ್ತೆ EMF ಮತ್ತು ಕರೆಂಟ್ ಪ್ರೊಡ್ಯೂಸ್ ಆಗ್ತಾರೆ. Again EMF and current will get produced in that. Correct? So here flux was increasing, so current got produced. Current and EMF got produced. Here flux is decreasing, again the current and EMF are getting induced. So in which direction this current will be? That is what we have to decide. Here, what is happening to the flux? It is decreasing, right? That flux is due to the inverse magnetic field. ಇಲ್ಲಿ ಎಕ್ಸಿಸ್ಟಿಂಗ್ ಅಥವಾ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ನಮಗೆ ಇನ್ವರ್ಸ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಏನಿತ್ತಲ್ಲ ಅದು ಇನ್ಕ್ರೀಸ್ ಆಗತ್ತಿಲ್ಲ, ಇಟ್ ವಾಸ್ ಇನ್ಕ್ರೀಸಿಂಗ್. ಹಿಯರ್ ದ ಇನ್ವರ್ಸ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಇಸ್ ಡಿಕ್ರೀಸಿಂಗ್. ಸೊ ದಟ್ ಇಂಡ್ಯೂಸ್ಡ್ ಕರೆಂಟ್ ಅಂಡ್ ಇಂಡ್ಯೂಸ್ಡ್ EMF will, the character of induced EMF and induced current is like that key. They will not let to increase also, they will not let to decrease also. Increase ಆಗಕತ್ರ increase ಆಗ್ಲಿಕ್ಕೆ ಬಿಡಂಗಿಲ್ರಿ, decrease ಆಗಕತ್ರ decrease ಆಗ್ಲಿಕ್ಕೆ ಬಿಡಂಗಿಲ್ಲ. That type of character it has. So here it was increasing, so it started opposing that inverse magnetic field to increase, so it was in outwards, so we took the induced magnetic field outwards. Here the inverse magnetic field is decreasing, so we should not let it to decrease. ಅದು ಡಿಕ್ರೀಸ್ ಆಗ್ಲಿಕ್ಕೆ ಬಿಡಬಾರ್ದು, ನಾವು ಅದನ್ನ ಸಪೋರ್ಟ್ ಮಾಡಬೇಕು. ಸೊ ಟು ಸಪೋರ್ಟ್ ದಟ್ the induced magnetic field must be in the same direction of that existing magnetic field. ಇಲ್ಲೇ ಇನ್ವರ್ಸ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್, ಎಕ್ಸಿಸ್ಟಿಂಗ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಏನಿತ್ತು ಅದು ಇನ್ಕ್ರೀಸ್ ಆಗತ್ತೈತ್ರಿ. ಸೊ ಅದ್ರದ್ದು ಇನ್ಕ್ರಿಮೆಂಟ್ ನಿಲ್ಲಿಸಲಿಕ್ಕೆ ನಾವು ಔಟ್ವರ್ಡ್ಸ್ ಇಂಡ್ಯೂಸ್ಡ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ತಗೊಂಡ್ವಿ. ಇಲ್ಲಿ ಡಿಕ್ರೀಸ್ ಆಗತ್ತದ್ರಿ, ಸೊ ಆ ಡಿಕ್ರಿಮೆಂಟ್ ಅನ್ನು ಸಪೋರ್ಟ್ ಮಾಡ್ಲಿಕ್ಕೆ ನಾವು ಸೇಮ್ ಡೈರೆಕ್ಷನ್ ಒಳಗೆ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಅನ್ನು ತಗೋಬೇಕು, right? Okay, if the induced magnetic field is inverse, then current has to be clockwise in direction. Hence in this coil the current will be clockwise in direction, right? So here the current will be clockwise in direction. This is how we have to decide the direction of induced current. Okay, next, see, whenever idantu namage elrigu gottade, whenever the north pole is brought close to the coil, that coil will behave like north pole only. And if it is behaving like north pole, current in that coil will be anti-clockwise in direction. If the north pole is taken away from the coil, it will behave like south pole. If it is south pole, then the current in the coil will be clockwise in direction. If a south pole is brought close to the coil, it will behave like a south pole, current will be clockwise. If the south pole is taken away, it will behave like north pole and anti-clockwise current will be produced in that. Right? Okay, that we already know. If we are moving close, it will behave like a like pole. If we are moving away, it will behave like a unlike pole. Right? This is what happens. Next, you concentrate on this now. Listen. Here we are having the magnetic field. Right? This much we are having the magnetic field. This is the region of the magnetic field. Correct? So this is the region where the magnetic field is present. So what we are doing here is, we have taken a square loop, we are moving that square loop like this inside the magnet and we are taking it away from the magnetic field. So when the square loop is entering inside the magnetic field, its flux changes. Flux changes andre ena, its flux increases. Yakandre idu horgade iddaga adralage magnetic flux 0 ittu. No magnetic field lines were passing in that when the loop was outside. Now when it starts entering the magnetic field, one by one magnetic field lines will start passing through it. It means its flux starts increasing. So since flux is changing, EMF and current will get induced. Once it comes completely inside the magnetic field, a square loop ಒಮ್ಮೆ magnetic field ಒಳಗಡೆ complete ಆಗಿ ಬಂತಪ್ಪ ಅಂತಂದ್ರೆ ಅದರದ magnetic flux change ಆಗಂಗಿಲ್ಲ. It remains constant. Right? When it is here, there is one line. When it comes here, there is one line. When it comes here, there is one line. When it comes here, there is one line. So every time its line is same. Its flux is same. So if flux remains constant, then there is no induced EMF and induced current in the coil. Right? And when it is moving out, here flux was increasing and here flux will be decreasing. Illa namagu flux decrease agtade. So even if the flux increases, we say flux is changing. Even if the flux decreases, we say flux is changing. So when the flux is decreasing, we again say flux is changing, and again the EMF and current will get induced. But this time the induced current will be in opposite direction of the entry time. When it was entering the field, at that time what was the direction of the current? In the opposite direction the current will be induced here. In middle, when it is completely inside the field, there will be no magnetic flux. But here the speed of that coil has to be uniform, constant, right? It should not keep changing. Okay. Next, when you drop a bar magnet along the axis of a coil, you want the coil the axis ಮೇಲೆ ನಾವು ಒಂದು bar magnet ಅನ್ನು ಬಿಡಾತೀವಿ. See, if there is no coil and if you lose a magnet, it will fall freely downwards, right? ಅದು freely downwards ಕೆಳಗಡೆ ಬೀಳ್ತೈತೆ ನಮಗೆ, right? ಅದರ velocity increase ಆಗುತ್ತಾ ಹೋಗ್ತದೆ, ಅದಕ್ಕೆ acceleration constant ಬರ್ತದೆ, and its acceleration will be equal to g because it is a freely falling body. That all happens. But when there is the coil in the path of that magnet, what happens? When this magnet comes close to the coil, now this coil will behave like a north pole. This coil kuda namaga north pole tara behave ಮಾಡಿ ಇದ್ರೊಳಗೆ ನಮಗೆ anti clockwise direction ಒಳಗೆ current produce ಆಗ್ತದೆ. Correct? Then if this is also north, then there will be the opposition in between them, repulsion between them, due to which its speed will decrease, and hence acceleration of that magnet will become less than acceleration due to gravity. When it has passed out from this, ಹಂಗಂತೇಳಿ ಅದನ್ನ ಎಲ್ಲಂಗಿಲ್ಲ, ಅದು ಇದ್ರೊಳಗಿಂದ ಪಾಸ್ ಆಗಿ ಬರ್ತದ್ರಿ. When it passes out from that, ಆ coil ದಾಗಿಂದ ಪಾಸ್ ಆಗಿ ಈ ಕಡೆ ಬಂದ ಕೂಡಲೇ ನಾವು south pole is close to that. South pole is close to that, right? So this coil will behave like a north pole now. ಇದೀಗ north pole ನೋಡ್ರಿ. When it was coming near, it behaved like a north pole and it started opposing it. When it is going far, it behaves like a north pole and it starts attracting it. ಅದನ್ನ ಅಟ್ರಾಕ್ಟ್ ಮಾಡ್ಕೊಳ್ಳಿಕ್ಕೆ ಶುರು ಮಾಡ್ತದ್ರಿ. So again there is the opposition to the motion of the magnet. So again acceleration will be less than acceleration due to gravity. So if a magnet is falling without a coil, it will fall freely. Its acceleration will be g. If the magnet is falling from the coil, its acceleration will be less than g. ಅದರದ acceleration less than g ಇರ್ತದೆ. Next ಇಲ್ಲಿ ನೋಡಿ, if the coil is having a cut, it is not complete 360 degree coil. Cut ಆಗಿತ್ತಪ್ಪ ಅಂತಂದ್ರೆ there the magnet will fall freely and its acceleration will be equal to g, because here induced current in that coil will become zero, because to flow the current the coil is not complete. Namaga open circuit adre, open circuit means its resistance will be infinite and current will be zero in that circuit. That is called open circuit. It is open circuit only. Induced current is zero irtadre, but induced EMF will be there. Induced current is zero, but induced EMF will be there. Right? Okay, one more case. If an electron is moving beside the coil, ಇಲ್ಲಿ ನಮಗೊಂದು coil ಇದೆ and electron is moving from A to B, B to C. When electron moves from A to B, I mean when it is moving close to the coil, current in the coil will be in anti-clockwise direction. Standard result ಅದ ನೆನಪಿಟ್ಕೋಬೇಕು. And when electron is moving from B to C, away from the coil, current will change its direction. It was anti-clockwise, here it will become clockwise. So as the charged particle moves towards the coil and away from the coil, the direction of current reverses. Right? Okay, so remember these things. We'll go to the next concept now. EMF induced in a rotating coil. Whenever a coil is rotating in a magnetic field, right? ಇಲ್ಲಿ ನಮಗೆ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಚೇಂಜ್ ಆಗತ್ತಿಲ್ಲ, ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಕಾನ್ಸ್ಟೆಂಟ್ ಅದ, ಜಸ್ಟ್ ಏನೋ ಒಂದು ಕಾಯಿಲ್ ನಮಗೆ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಒಳಗೆ ರೋಟೇಟ್ ಆಗತ್ತೈತಿ. ಸೊ ಇಫ್ ಅ ಕಾಯಿಲ್ rotates in the magnetic field, its angle changes, its orientation changes. Due to change in its orientation, the flux changes, and if flux changes, EMF will get induced in that. So the EMF induced in the rotating coil is E equal to NBA omega sin theta, right? Or you can also write it as E naught sin theta. E naught means it is NBA omega. Theta means you can take it as omega t also, right? Omega t, theta. Next, induced charge. Induced charge. Induced charge Q is equal to N d pi by R. Number of turns into d pi, change in flux divided by resistance. It is independent of time, charge, right? Motional EMF. See, what do you mean by this motional EMF? Motional EMF means it is the EMF which is produced in a rod, in a straight conductor or in a rod due to the motion of that rod in the magnetic field. Due to the motion of that rod in the magnetic field. See, here we have taken a rod which is like this. Magnetic field is inwards. Magnetic field is inwards. And that rod is moving perpendicular to the magnetic field. ಅವಾಗ ಈ ರಾಡ್ ಒಳಗೆ ನಮಗೊಂದು EMF ಇಂಡ್ಯೂಸ್ ಆಗ್ತದೆ. And that EMF is given by E is equal to B into L into V. Right? This is called motional EMF. See, this motional EMF will get produced only when it cuts the magnetic field lines perpendicularly. Right? ಅಂದ್ರೆ ಈಗ ನಮಗೆ ಇದು ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಡೈರೆಕ್ಷನ್ ಅದ ಅಂತ ಇಟ್ಕೊಡಿ. ಈ ರಾಡ್ ನಮಗೆ ಈ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಲೈನ್ಸ್ ಕಟ್ ಮಾಡಬೇಕು. ಇಟ್ ಶುಡ್ ಕಟ್ ದ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಲೈನ್ಸ್ ಲೈಕ್ ದಿಸ್. ರೈಟ್? ಇಫ್ ಇಟ್ ಇಸ್ ನಾಟ್ ಕಟಿಂಗ್ ದ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಲೈನ್, ಇಫ್ ಇಟ್ ಇಸ್ ಮೂವಿಂಗ್ ಲೈಕ್ ದಿಸ್, ಈ ತರ ಅದಕ್ಕೆ ಪ್ಯಾರಲಲ್ ಆಗಿ ಮೂವ್ ಆಗತ್ತಪ್ಪ ಅಂದ್ರೆ ಅದ್ರೊಳಗೆ EMF ಇಂಡ್ಯೂಸ್ ಆಗುದಿಲ್ಲ, ಮೋಷನಲ್ EMF ಇಂಡ್ಯೂಸ್ ಆಗುದಿಲ್ಲ. ಇಟ್ ಶುಡ್ ಕಟ್ ದ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಲೈನ್ಸ್ ಪರ್ಪೆಂಡಿಕ್ಯುಲರ್, ದೆನ್ ಓನ್ಲಿ ಮೋಷನಲ್ EMF will get induced. Correct? Next, if that rod is not exactly perpendicular and nor even it is parallel to the field, perpendicular ಇಲ್ಲ parallel ಇಲ್ಲ, ಅವಾಗ induced EMF will be BLV sin theta. When it is exactly perpendicular, BLV. When it is not exactly perpendicular, BLV sin theta. Here, if the rod is moving like this, ಇಲ್ಲಿ ನೋಡ್ರಿ magnetic field inverse ಅದ, the rod is moving like this. It means it is not cutting the magnetic field lines perpendicularly. That's why EMF induced here will be 0. ಇದ್ರೊಳಗೆ ನಮಗೆ EMF induced 0 ಇರ್ತದೆ. Next ನೋಡ್ರಿ, EMF induced in the axle of the car. Axle of the car ಅಂತಂದ್ರೆ ಏನ, ಕಾರದ ಎರಡು ವೀಲ್ ನಡುವೆ ಏನ್ ರಾಡ್ ಇರ್ತದ್ರಿ ಅದಕ್ಕೆ axle ಅಂತ ಕರೀತಾರೆ. ಟ್ರೈನ್ ಎರಡು ವೀಲ್ಸ್ ನಡುವೆ ಏನ್ ರಾಡ್ ಇರ್ತದೆ ಅದಕ್ಕೆ axle ಅಂತ ಕರೀತಾರೆ. So in all these cases, car, train, tips of the wings of the aeroplane, okay, ಆ ಏರೋಪ್ಲೇನ್ ಏನೆರಡು ವಿಂಗ್ಸ್ ಇರ್ತಾವ ಅದನ್ನ ಒಂದು ರಾಡ್ ಅಂತ ತಿಳ್ಕೊಂಡು ಅದ್ರೊಳಗೆ ಎಷ್ಟು EMF ಇಂಡ್ಯೂಸ್ ಆಗಿದೆ ಅಂತ ಕೇಳಿದ್ರೆ, in all these three cases, car, train, plane, aeroplane, EMF induced will be BV into L into V. BV means it is vertical component of Earth's magnetic field. It is BV. Subscript ಒಳಗೆ V ಬರ್ತದೆ ನಮಗೆ, right? It is vertical component of Earth's magnetic field. Question ಒಳಗೆ ಕೊಡ್ತಾರೆ ನಿಮಗೆ ಅದನ್ನ. Vertical component of Earth's magnetic field into length into velocity. Right? That's all about motional EMF. Next, EMF induced in a rotating rod or a disc. Rotating rod or a disc. See, here we have taken inverse magnetic field and we have taken a rod here. We have taken a rod here whose length is L. Whose length is L. And one end of the rod is fixed. One end ನಮಗೆ ಫಿಕ್ಸ್ ಅದ, ಇನ್ನೊಂದು ಎಂಡ್ ನಮಗೆ ರೋಟೇಟ್ ಆಗತ್ತದ್ರಿ. Another end of the rod is rotating like this. See, one end is fixed, another end is rotating like this. ಈ ತರ ನಮಗೆ ರೋಟೇಟ್ ಆಗತ್ತದ್ರಿ. ಕರೆಕ್ಟ್? ಸೊ ಇಫ್ ಇಟ್ ಇಸ್ ರೋಟೇಟಿಂಗ್ ಲೈಕ್ ದಿಸ್, ಅಥವಾ ಇಲ್ಲೊಂದು ನಾವು ಫುಲ್ ಡಿಸ್ಕ್ ತಗೊಂಡಿವಿ, ಡಿಸ್ಕ್ ಅಂದ್ರೆ ಪ್ಲೇಟ್ ಅಂದಂಗೆ, ಅಂಡ್ ಇಫ್ ಇಟ್ ಇಸ್ ರೋಟೇಟಿಂಗ್, ದ ಡಿಸ್ಕ್ ರೇಡಿಯಸ್ ಆಫ್ ದ ಡಿಸ್ಕ್ ಇಸ್ R and this is rotating, then EMF induced in this rotating disc and rotating rod. Rod should be rotating in such a way that axis of rotation should be at one end. Axis of rotation should be at one end, right? ಈ ತರ ಇರಬೇಕು ನಮಗೆ. So in these both cases, induced EMF will be half BL square omega. It is angular frequency, or half BR square omega. L ಅಂದ್ರೆ length of the rod, R ಅಂದ್ರೆ radius of that disc. Half BL square omega or half BR square omega, or B into F into A. right? These are the formulas for calculating induced EMF in rotating disc and rotating rod. Next, if the rod is rotating in the magnetic field in such a way that its axis of rotation is at the center of the rod, midpoint of the rod. ಅಂದ್ರೆ ನಮಗೆ rod the axis of rotation ಹಿಂಗದರಿ, it is rotating like this now. ಈ ತರ ನಮಗೆ rotate ಆಗತ್ತಿತ್ತು ಅಂತ ಇಟ್ಕೊಳ್ಳಿ. Axis is at the center and it is rotating like this. In this case, EMF induced in this rod will be 0 because ಈ ಕಡೆ ಏನ್ ನಮಗೆ EMF induce ಆಗಿರ್ತದ ಆ EMF ಮತ್ತು EMF ಎರಡು ನಮಗೆ ಅಪೋಸಿಟ್ ಇರ್ತವೆ, ಕ್ಯಾನ್ಸಲ್ ಆಗಿ EMF becomes 0. And the same formula is applied for EMF between axle and rim of the spoked wheel. Spoked wheel ಅಂದ್ರೆ ಸೈಕಲ್ ವೀಲ್ ಇರ್ತಾವಲ್ಲ, ಸೈಕಲ್ ವೀಲ್ಸ್ ಹೆಂಗಿರ್ತಾವ್ರಿ, ಸಣ್ಣ ಸಣ್ಣ ರಾಡ್ಸ್ ಇರ್ತಾವಲ್ಲಿ ಸೈಕಲ್ ವೀಲ್ಸ್ ಒಳಗೆ, ರೈಟ್? ಸೊ ಆ ತರದ ವೀಲ್ ಬಂದಾಗ ಎಕ್ಸಿಲ್ ಆಫ್ ದ ವೀಲ್, ಸೆಂಟರ್ ಆಫ್ ದ ವೀಲ್ ಮತ್ತು ರಿಮ್ ಆಫ್ ದ ವೀಲ್ ಅಲ್ಲಿವರೆಗೂ ಅವೇನ್ ನಮ್ಗೆ ರಾಡ್ಸ್ ಇರ್ತಾವ, ಆ ರಾಡ್ಸ್ ಒಳಗೆ ಎಷ್ಟು EMF ಇಂಡ್ಯೂಸ್ ಆಗಿದೆ ಅಂತ ಕೇಳಿದ್ರೆ ಅಗೇನ್ ಯು ಹ್ಯಾವ್ ಟು ಅಪ್ಲೈ ದ ಸೇಮ್ ಫಾರ್ಮುಲಾ, half BL square omega, right? Okay, because those are also rotating rods only. Okay, so the effective itself will be that much. Next, we'll go for self-induction. See, we know very well, self-induction means in a coil, whenever you pass a changing current means its magnitude should be changing. For example, 1 ampere, 2 ampere, 3 ampere, 4 ampere, 5 ampere, like this. Either it should be increasing, or 5 ampere, 4 ampere, 3 ampere, it should be decreasing. Something should be happening there. So, ಈ ತರದೊಂದು varying current ಅಥವಾ changing current, if you pass through a coil, flux of the coil will change. And if flux of the coil changes, in the same coil, EMF and current will get induced, right? So, in which coil we are passing the changing current, in the same coil, EMF and current have got produced. This phenomenon is called self-induction. Here, magnetic flux of this coil will be directly proportional to current. If you increase the rate of increment of the current, flux increases, right? That's why we say flux is directly proportional to I. And when we remove the proportionality symbol, we'll get a constant called as coefficient of self-inductance, L, coefficient of self-inductance. And this L, coefficient of self-inductance, is measured, its SI unit is Henry. Its SI unit is Henry inductance, right? Okay, so in this case, the EMF induced is given by E is equal to minus L di by dt. The EMF induced in this coil is E equal to minus L di by dt. Next, if current is increasing, then this rate of change of current, di by dt means it is rate of change of current. That rate of change of current should be taken positive when the current in the coil is increasing, and it should be taken negative when the current in the coil is decreasing, right? Next, self-inductance of a solenoid. Remember these formulas. Solenoid formula antu 100% ನೆನ್ಪಿಟ್ಕೋಬೇಕು. Self-inductance of the solenoid is mu naught n square AL. If a medium is substituted, mu naught into mu r n square AL. ಅಂದ್ರೆ solenoid ಒಳಗಡೆ ಏನಾದರೂ ಒಂದು ಐರನ್ ರಾಡ್ ಏನಾದರೂ ಒಂದು ಮಟೀರಿಯಲ್ ಸಬ್ಸ್ಟಿಟ್ಯೂಟ್ ಮಾಡ್ಕೊಂಡ್ರೆ ಅದರ ರಿಲೇಟಿವ್ ಪರ್ಮಿಯಾಬಿಲಿಟಿ ಒಂದು ಮಲ್ಟಿಪ್ಲೈ ಮಾಡ್ಕೋಬೇಕು ನೀವು, ಕರೆಕ್ಟ್? ಓಕೆ, so L is equal to mu naught n square AL or mu naught capital N square A divided by L. What is the difference between small n and capital N? Small n is number of turns per unit length. Capital N is total number of turns in the coil, right? That is the difference. So small n is equal to capital N divided by L, number of turns per unit length. This is the equation of self-inductance of the solenoid. Self-inductance of a circular coil, mu naught pi n square r divided by 2. Mu naught pi n square r divided by 2. That is self-inductance of circular coil. So remember, next we'll go for energy stored in inductor. Energy stored in inductor is half Li square. Energy stored in capacitor is half Cv square. This is magnetic energy stored in the form of magnetic field. Half Li square is the magnetic energy stored in the form of magnetic field inside the solenoid. Half Cv square is the electric energy stored in the form of electric field in between the plates of the capacitor, right? Next, energy density. Energy density is B square by 2 mu naught. B square divided by 2 mu naught. This is the energy density of that coil. Combination of inductors. If the inductors are connected in series, effective inductance will be L1 plus L2. If they are connected in parallel, effective inductance will be L1 into L2 by L1 plus L2. Right? Effective series resistance, effective parallel resistance is formula type adare. Athwa effective parallel capacitance, effective series capacitance format olaga namagu formulas adav. Next, mutual inductance. See, self inductance andre there was only one coil in the same coil current was changing, in the same coil current and EMF was induced. That is self-inductance. Mutual inductance means here we'll be having two coils. One is first coil, this is first coil and this is second coil. When you pass a changing current in the first coil, when you change the current in the first coil, flux of the second coil will change. Due to the change in the current of the first coil, flux of the second coil will change. Second coil ಒಳಗೆ ನಾವು current ಅನ್ನು pass ಮಾಡತ್ತಿಲ್ಲ. First coil ಒಳಗೆ pass ಮಾಡತ್ತೀವಿ, ಆ current ಅನ್ನು ನಾವು change ಮಾಡತ್ತೀವಿ. Because of that, the second coil will change its flux. Since the flux of the second coil is changing, an EMF and current will get induced in the second coil. Right? So this EMF and current which are induced in the second coil is due to mutual induction phenomenon. Current in one coil has changed. Due to that, flux of another coil got changed. And EMF as well as current got induced in that second coil. That phenomenon is mutual inductance. ಹಂಗಂತೇಳಿ ಇಲ್ಲಿ ಫಸ್ಟ್ ಕಾಯಿಲ್ ಒಳಗೆ ನಮಗೆ ಫ್ಲಕ್ಸ್ ಚೇಂಜ್ ಆಗಿಲ್ಲ ಅಥವಾ ಫ್ಲಕ್ಸ್ ಕಾಯಿಲ್ ಒಳಗೆ EMF ಮತ್ತು ಕರೆಂಟ್ ಫಸ್ಟ್ ಕಾಯಿಲ್ ಒಳಗೆ ಇಂಡ್ಯೂಸ್ ಆಗಿಲ್ಲ ಅಂತಲ್ಲ, ಅಲ್ಲೂ ಇಂಡ್ಯೂಸ್ ಆಗಿರ್ತಾವೆ. Flux of first coil will also change. If you change the current in the first coil, flux of first coil will also change. Flux of second coil will also change. And due to the change in flux of the first coil, whatever EMF and current are getting induced, that is due to the phenomenon of self-induction. And due to the change in the flux of the second coil, whatever EMF and current will get induced, that is due to the phenomenon of mutual induction. Idu mutual induction ದಿಂದ produce ಆಗಿದ್ದು, ಇದು self-induction ದಿಂದ produce ಆಗಿದ್ದು. So here also the flux will be directly proportional to current in the first coil. Idu flux of the second coil. Idu current in the first coil. Right? So the flux of the second coil is directly proportional to the current in the first coil. So flux of the second coil will be equal to mutual inductance of first and second coil into current in the first coil. Right? So this is the flux. This is the flux. Right? In nodri number of turns ನೀವು multiply ಮಾಡ್ಕೋಬೇಕು. Second coil ಒಳಗೆ number of turns multiply ಮಾಡ್ಕೊಂಡ್ರೆ ನಡೀತದೆ. Next. EMF induced by this mutual induction. EMF induced by self-induction was minus L di by dt. EMF induced by mutual inductance is minus M di by dt. M is coefficient of mutual inductance. Right? Next, mutual induction of coaxial solenoids. Coaxial solenoids. Coaxial solenoids means there are two solenoids here. Okay, we'll be having two solenoids of equal length and different cross-sectional area. Two solenoids of equal length and different cross-sectional area. Right? So we'll be having two solenoids here of equal length and different cross-sectional area. Right? So length is same of both the coils, but radius, I mean cross-sectional area is different. Cross-sectional area is different. Let the radius of inner coil be taken as small r. Right? So in this case, the mutual inductance of these coaxial solenoids is given by mu naught n1 into n2 into a into L. Number of turns per unit length in first coil, number of turns per unit length in the second coil. Or in terms of total number of turns, if you want to write, it will be mu naught n1 n2 a divided by L. Mu naught n1 n2 a divided by L. Mutual inductance of concentric circular coils. Either solenoids or coaxial solenoids. Now concentric circular coils. Mu naught n1 n2 pi r square divided by 2r. Mu naught n1 n2 pi r square divided by 2r. Remember, this pi r square is the area of the inner coil. Area of the inner coil. Here also, this is the area of the inner solenoid. Smaller solenoid anta ಏನು ಕರಿತೀವಲ್ಲ ಅಥವಾ inner solenoid ಅಂತಾರೆ. It is the area of that. Correct? Okay. So we have to always take the areas of smaller coils or smaller solenoids here. That's all about mutual inductance. Next. Relation between coefficient of mutual inductance and the self-inductance of the two coils. M is equal to K into root of L1 into L2. This is the relation between mutual inductance and the coefficient of the two coils. Here K is called coefficient of coupling. K is called coefficient of coupling. If the solenoids are coaxial, it is called tight coupling and the value of K will be 1. If the solenoids are having different axes, they are not coaxial, then it is called loose coupling. Its value of K will be less than 1. If the axes of the solenoids are perpendicular, then they are said to be having no coupling. K is equal to 0. Perpendicular or either opposite order, its coupling value will be 0. There is no coupling there. Okay. So this will be done. Tight coupling will be done to reduce flux leakage. Flux leakage reduce madlike this tight coupling will be done. Okay. Well, we'll go for the next concept now. Growth of current in LR circuit. See, growth of current in LR circuit means we'll be taking an inductor and a resistor connected in series here. When you connect a source to this, and when current suddenly increases in this circuit, when current, ನೀವು battery connect ಮಾಡೋಕ್ಕಿಂತ ಮುಂಚೆ current 0 ಇತ್ತು, current was 0. Before connecting the battery, the current in the circuit was 0. And after connecting the battery, the current suddenly got raised. So when it is increasing from 0 to I, at that time, this inductor will start opposing the increment of that current. A current in increase ಏನಾಗ್ತಿರ್ತದಲ್ಲ 0 ದಿಂದ I ಗೆ, ಆ increment of current in oppose ಮಾಡ್ತಿದ್ರೆ. So in that phase, how much will be the current in the circuit? That is this formula. I is equal to I naught. I naught is the maximum current. I is equal to I naught into the bracket 1 minus e raised to minus r by L into t. T is the time instant. Right? ಯಾವ instant again time current ನಿಮಗೆ ಬೇಕಾಗಿದೆ. In the same way, when you remove the battery again, the current will decrease again from maximum to 0. So when it is again changing, when the current is decreasing from maximum to 0, again the current, again this will start opposing. If the current is constant, this is not going to oppose. ಇದು ನಮಗೆ ಒಟ್ಟ ಅಪೋಸ್ ಮಾಡಂಗಿಲ್ಲ, ನಾರ್ಮಲ್ ಕಂಡಕ್ಟರ್ ತರ ಬಿಹೇವ್ ಮಾಡ್ತೈತ್ರಿ. ಕಾನ್ಸ್ಟೆಂಟ್ ಕರೆಂಟ್ ಇದ್ದಾಗ ಅಪೋಸ್ ಮಾಡೋದು ರೆಸಿಸ್ಟರ್. But when there is change in current, at that time this will start opposing. Whether increment of the current ಅಥವಾ decrement of the current ಆಗತ್ತಿತ್ತಪ್ಪ ಅಂತಂದ್ರೆ this will start opposing. This will start opposing. Sorry, that was a balloon. Okay, so decay of current in LR circuit. Decay of current in LR circuit, it means when the current is decreasing. This is when the current is increasing. So it is I is equal to I naught e raised to minus r by L into t. That is I is equal to I naught 1 minus e raised to minus r by L into t. Correct? Well, so remember the formulas. Formula ಗೊತ್ತಿದ್ರೆ ಸಾಕು, directly ನೀವು calculate ಮಾಡಬಹುದು. ಆ ತರದ questions ಇರ್ತಾವೆ. Okay, we'll go for the last concept of this chapter now, that is transformer. We know very well, transformer works on the principle of mutual inductance. Mutual induction ಒಳಗೆ ಎರಡು coil ಇರಲೇಬೇಕು. So here there are two coils, primary, secondary. Whatever input you give or input voltage, input current, input power ಅಂತ ಏನು ಹೇಳ್ತಾರೆ, that is all related to primary. Output current, output voltage, output power ಅಂತ ಏನು ಹೇಳ್ತಾರೆ, that is all related to secondary. Right? So the voltage, current and number of turns in primary are represented by Vp, Ip and Np. The voltage, current and number of turns in the secondary are called Vs, Is and Ns. Okay, so these are the values related to the primary and secondary coils of the transformer. See, transformation ratio, it is the ratio of voltage of secondary divided by voltage of primary, number of turns in secondary by number of turns in primary, equal to current in primary by current in secondary. See, voltage and number of turns, these both are secondary by primary, but current is primary by secondary. Current is primary by secondary, right? So for step-up transformer means which converts low voltage to high voltage, that is step-up. Its value of K will be greater than 1. K value of greater than 1 irtadre. Number of turns in secondary will be greater than number of turns in primary for step-up transformer. For step-down transformer, which converts high voltage to low voltage, here what happens is K will be less than 1 and number of turns in primary will be greater than number of turns in secondary. Primary ಒಳಗೆ ಜಾಸ್ತಿ ಇರ್ತಾವೆ. Next, efficiency of a transformer. Efficiency means it is output power upon input power. What is power? Power means voltage into current, right? So output power means output is related to secondary. So output power means it will be equal to product of voltage of output coil, current of output coil. It means Vs into Is, voltage of secondary, current of secondary. Input power means it is the product of primary voltage, primary current, Vp into Ip. Right? Next, for ideal transformer, input power and output power both will be equal. It means Vs into Is will be equal to Vp into Ip. This is 1 irtadri. Input power and output power both will be equal. Input power and output power both are equal in the sense Vp into Ip will be equal to Vs into Is. Will be equal to Vs into Is, right? And efficiency will be equal to 1. 1 ಅಂತಂದ್ರೆ 100%. Ideal transformer ಮಾತ್ರ efficiency 100 ಇರುತ್ತೆ. Practically there is no transformer which is 100% efficient. So this is just an ideal concept, ideal theoretical concept ಅಷ್ಟೇ, right? ಇದರದ efficiency ಮಾತ್ರ 1 ಇರ್ತದೆ. 1 ಅಂದ್ರೆ 100%, 0.9 ಅಂದ್ರೆ 90%, 0.8 means 80%, 0.7 means 70%. So practically the efficiency of the transformers will always be less than 1. ಅಂದ್ರೆ less than 100% ಇರ್ತದೆ. right? So that is all about transformer. Okay, that's all about electromagnetic induction. Dear students, if you like the content of this channel, please don't forget to subscribe the channel and share the videos and share the channel with your friends. Please keep supporting and keep watching the channel. We'll meet again in the next video with the next chapter. Thank you so much. If you need anything else, please put a comment. I'll try to make the video on that for sure. Right? Thank you. Please keep watching and supporting.